Hold a compass, and the needle swings north, pulled by a field you cannot see. That needle is a small magnet, and so, it turns out, is one of the tiniest things we know of. A particle called the muon spins, and as it spins, it behaves like a faint magnet of its own. When physicists measure exactly how strong that magnetism is, it comes out a hair larger than the leading theory predicts. That hair-thin excess is the crack in the title, and the theory it presses against is the standard model, the closest thing we have to a full account of what everything is made of. Physicists call the measurement G2, and tonight we'll build up to it slowly, one plain step at a time. If this calm kind of wondering suits you, take a moment to subscribe. Where could that extra magnetism come from? Take a compass out of a drawer and set it flat on a table. The needle drifts, hunts a little, and settles pointing north. Nothing touches it. It is pulled by the magnetic field of the whole planet, a field you cannot see or feel, yet the needle finds it every time. That needle is a small magnet, and the earth beneath it is a far larger one, and the two quietly line up. This gentle pull is where our whole story begins, because the muon at the end of it behaves, in its own tiny way, exactly like that needle. For a long time, people thought magnetism and electricity were separate things. Then, in the year 1820, a Danish scientist named Hans Christian Ørsted was giving a lecture and noticed that a compass needle twitched whenever he switched on a nearby electric current. Moving electric charge, it turned out, makes magnetism. André-Marie Ampère in France worked out the rule soon after. A loop of current, a ring of moving charge, creates a magnetic field, and it behaves like a little bar magnet with a north and a south face. So a magnet is really charge in motion. Iron is magnetic because countless electrons inside it are, in a sense, circulating in step. Once you know this, a natural picture forms. If you took a single speck of electric charge and spun it, the spinning charge would trace tiny loops, and those loops would make it a mini magnet of its own. The strength of that little magnet has a name. Physicists call it the magnetic moment. It measures how hard the object twists when you place it in a magnetic field, the way the compass needle twists toward north. Hold that word, magnetic moment, because it is the quiet hero of everything that follows. A larger magnetic moment means a stronger response, a firmer tug. A smaller one means a fainter tug. Every magnet, from a fridge magnet to a spinning particle, can be summed up by this single number, its readiness to line up with a field. Now shrink the picture down. Inside every atom sit electrons, each carrying a sliver of negative charge. If an electron were a tiny charged marble, spinning on its axis, it would make its own magnetic field, and it would have its own magnetic moment. That was the reasonable guess in the early days of atomic physics. Picture a child's top, painted with a smear of static charge whirling on a desk. As it spins, the charge goes round and round, and a faint magnetism appears along the axis of the spin. The electron, people imagined, might be something like that top. The comparison is friendly, and it will carry us a little way, but the electron is not really a spinning marble. It has no measurable size. As far as any experiment has ever shown, it is a point, with no surface to paint charge onto, and no axis in the ordinary sense. So the neat image of a whirling charged ball breaks the moment you look closely. And yet the electron truly does act like a magnet. It has a magnetic moment. It twists in a field. Something about it carries the magnetism that the spinning marble story only pretended to explain. That gap between the simple picture and the real behaviour is the seam we will follow for the next 2 hours. The magnetic moment of a particle is a real, measurable thing, and it is also one of the most precisely known numbers in all of science. To understand why a muon's magnetism could crack our deepest theory of matter, we first have to understand the electron's magnetism. And to do that, we have to ask a strange question. If the electron is not a spinning ball, then how does it carry a magnet at all? And how strong is that magnet meant to be? In the year 1922 in Frankfurt, two physicists set up an experiment that looked almost too simple to matter. Otto Stern and Walter Gerlach heated silver in a small oven until single atoms streamed out in a thin beam. They sent that beam between the poles of a specially shaped magnet, one that made the magnetic field stronger on one side than the other. Then they let the atoms strike a glass plate and watched where they landed. If the tiny atomic magnets could point in any direction, as an ordinary compass needle can, the beam should have smeared into a single broad band on the plate. That is what everyone expected. Instead, the silver split cleanly into two separate spots, one deflected up, one deflected down, with a gap between them. The atoms behaved as if their inner magnetism could only choose one of two settings, up or down, and nothing in between. Nature, at this scale, came in steps. It took a few years to understand what the two spots meant. In 1925, two young Dutch physicists, George Uhlenbeck and Samuel Goudsmit, proposed that the electron carries a kind of built-in rotation, an intrinsic angular momentum, which they called spin. Spin gives the electron its magnetic moment. The two spots in the silver beam were the two possible orientations of a single electron spin in each atom, pointing along the field or against it. The word spin is a comfortable handle, and it is worth keeping, but it hides a strange fact. The electron is not actually turning. It has no size to turn, no surface, no measurable radius. If you tried to picture a ball small enough to be an electron yet spinning fast enough to make the right magnetism, its surface would have to move faster than light, which nothing can do. So spin is real angular momentum and real magnetism, carried by something with no moving parts. It is a property as basic as charge or mass, one the electron simply has. Here is where the numbers start to matter. Physicists describe the link between a particle's spin and its magnetism with a single quantity called the g-factor. Think of the g-factor as a dial that sets how much magnetism you get for a given amount of spin. For a charge merely orbiting in a loop, the plain classical case, the dial sits at 1. If the electron spin were just ordinary rotation, you would expect its dial to read 1 as well. When Stern, Gerlach, and later experimenters measured it carefully, the electron's dial did not read 1, it read close to 2. The electron makes twice as much magnetism from its spin as the simple orbiting picture would allow. That factor of 2 was a genuine surprise. It said the spinning marble story was not just imprecise but wrong in a specific, measurable way, off by a clean factor. For a while, this factor of 2 was a fact without an explanation. It was measured, it was solid, and it sat there waiting. The g-factor of the electron was 2, and nobody could say from first principles why the dial landed there and not somewhere else. It looked like a number you would simply have to accept and write down, one of those brute facts the universe hands you without a reason. That is a frustrating place for a physicist to stand. A measured number with no theory behind it is an itch. Why 2 and not 1 and not 3? The answer would not come from tinkering with magnets or silver beams. It would come from a young Englishman working alone with a piece of paper, trying to force two great theories of the age, quantum mechanics and Einstein's relativity, to agree with each other. When he succeeded, the factor of 2 fell out of his equation on its own, unbidden, like a coin dropping into a slot. The young Englishman was Paul Dirac, and in the year 1928 he was 25 years old and famously silent. Colleagues joked that he spoke so rarely they invented a unit called the Dirac, 1 word per hour. He worked at Cambridge with a strange, austere faith that the right equation would also be beautiful, and that beauty in the mathematics was a sign you were near the truth. The problem Dirac set himself was a clash between two triumphs: quantum mechanics, newly built by Werner Heisenberg and Erwin Schrödinger, described the small world of atoms. Special relativity from Albert Einstein described anything moving near the speed of light. Each worked beautifully on its own. But the main quantum equation, Schrödinger's, treated space and time differently and quietly assumed particles moved slowly. It did not respect relativity. For a light, fast thing like an electron, that was a real flaw. Dirac wanted one equation that obeyed both sets of rules at once, that was quantum and relativistic in the same breath. After long effort, he found it. The Dirac equation, as it is now called, is short enough to write on a napkin, and it describes how an electron moves when both quantum mechanics and relativity hold. It was elegant in exactly the way Dirac trusted. Then came the gifts. The equation had not been built to explain spin at all. Dirac had not put spin in by hand. Yet when he examined his solutions, spin was already there, woven into the mathematics as an unavoidable consequence. The electron in his equation carried intrinsic angular momentum whether he wanted it to or not, and when he worked out how that spin would respond to a magnetic field, the G factor came out too. It came out as 2. That was the moment. The mysterious factor of 2, the measured number with no reason behind it, was suddenly explained. It was not an accident and not a brute fact. It was forced by the marriage of quantum mechanics and relativity. Any point particle of spin 1/2, which is the electron's kind of spin, must have a G factor of 2. The dial had to read 2. Dirac had found the reason. The equation gave one more gift, stranger than the rest. Its solutions came in pairs, and half of them described a particle with the electron's mass but the opposite, positive charge. Dirac hesitated, then predicted that such a particle must exist. In the year 1932, at the California Institute of Technology, Carl Anderson found it in cosmic rays and called it the positron. Antimatter had been predicted by pure equation and then discovered in the sky. Dirac's faith in beautiful mathematics had paid off twice over, so by the early 1930s the picture looked complete and clean. The electron was a point particle of spin 1/2. Its magnetic moment followed from Dirac's equation. Its G factor was exactly 2, a whole number, sharp and final. There was no fuzz on it, no decimal tail, no correction. 2, and done. It is worth pausing on how satisfying that was. A messy experimental number had been replaced by a clean theoretical certainty. The electron's magnetism was pinned to a simple integer that dropped out of the deepest equation anyone had. Physics does not often hand you a whole number and tell you it is exact. When it does, you tend to believe it. And for nearly 20 years, people did believe it. The G factor of the electron was 2, full stop, and the matter seemed settled. It took a war, a leap in measuring technology, and a pair of careful experimenters at Columbia to look closely enough to notice that the clean whole number was not quite whole. When they measured the electron's magnetism to enough decimal places, the sharp 2 grew a faint tail. The certainty had a crack in it, and the crack was real. The place was Columbia University in New York, and the year was 1947. The Second World War had just ended, and with it came a flood of new instruments born from wartime radar work, devices that could send and detect radio waves with astonishing control. Physicists turned these tools on the atom. For the first time, they could measure the energies inside atoms not to 2 or 3 digits, but to many. And at that depth, small things become visible that were invisible before. 2 experimenters at Columbia, Polycarp Cush and Henry Foley, used these methods to measure the electron's magnetic moment with new care. They watched how atoms responded to magnetic fields, reading the faint frequencies at which the atoms absorbed radio energy. Those frequencies depend directly on the electron's G factor. If Dirac was exactly right, the measurement would return 2, clean and sharp no matter how many digits they reached. It did not. Cush and Foley found that the electron's G factor was slightly larger than 2. The excess was small, close to 1 part in 1,000. Where Dirac's equation said 2, the real electron read about 2 and a tiny fraction more, the fraction landing near 2/1000ths. It was small, but it was solid, well outside any error in their careful setup. The clean integer had a decimal tail after all. To handle this excess neatly, physicists gave it its own name. They defined a quantity, the anomaly, as the amount by which the G factor exceeds 2, cut in half. Written plainly, the anomaly is G-2 divided by 2. For a perfectly Dirac electron, the anomaly would be 0. Cushon-Foley's electron had an anomaly of roughly 1,000th. This is the quantity, G-2, that gives our whole subject its name. The crack in Dirac's whole number is measured by how far G-2 rises above 0. 1,000th may sound like a rounding error, hardly worth the fuss. But in physics, the size of a discrepancy is only half the story. The other half is how sure you are of it. Cushon-Foley were very sure. Their number was steady, repeatable, and far too large to blame on a wobble in the apparatus. So the field faced a clear fact. Dirac's beautiful equation, which had earned everyone's trust, was not the last word. It gave the G-factor to a first excellent approximation, and then reality added a little more on top. This was not a failure of Dirac so much as a doorway. A number that theory cannot yet explain is precisely where new physics tends to hide. The electron was telling experimenters that something had been left out of the clean picture, something small but real, nudging the electron's magnetism upward by about 1,000th. Cush would receive the Nobel Prize in 1955 for pinning that nudge down. At almost the same time, and in the same building, another Columbia physicist named Willis Lamb found a second small crack. He measured a tiny shift in the energy levels of the hydrogen atom, a shift the plane theory said should not be there at all. The Lamb shift and the electron anomaly arrived together, two faint signals that the simple equations were missing a common ingredient. Both pointed in the same direction, towards something subtle happening around the electron that the old picture ignored. So by 1947 the stage was set for a reckoning. The electron's magnetism was measured to be a whisker more than Dirac allowed. The itch was back, sharper than before, and now it demanded a real cause, not just a name. The answer would come within a year, from a young theorist who realized the electron is never truly alone. It is always surrounded, always interacting, always dressed in a faint haze of activity that a truly empty space is not supposed to have. The young theorist was Julian Schwinger, and he was one of the quickest minds of his generation. He worked late and thought fast, and by 1948 he had built much of a new framework called quantum electrodynamics, the quantum theory of how charged particles and light interact. The name is a mouthful, so let us give it a plain handle. Quantum electrodynamics is the rulebook for electrons and photons, the particles of light, and how they trade energy back and forth. Schwinger's key insight was that an electron is never simply an electron. As it moves, it constantly emits and reabsorbs particles of light. It throws out a photon and catches it again, over and over, in a ceaseless private exchange. Each time it does this, the photon carries away a little momentum and brings it back, and the net effect slightly changes how the electron responds to an outside magnetic field. The electron's magnetism is not just its bare value. It is the bare value plus the sum of all these fleeting self-interactions. To picture it, imagine a person walking steadily across a room, but the person keeps tossing a ball into the air and catching it as they go. The tossing does not change where they are headed, yet it subtly alters their motion, a small lurch with each throw. The electron does something like this with photons the whole time, and the lurches add up to a measurable change in its magnetism. Schwinger calculated the leading effect of this constant self-interaction, the single most important term, the electron tossing and catching one photon. The answer he found was strikingly simple. The extra bit added to the anomaly equals a well-known constant of nature, the fine structure constant, divided by 2 times pi. In words, it is alpha over 2 pi. The fine structure constant, written alpha, is one of the most important numbers in physics. It measures how strongly charged particles and light interact, the strength of the electromagnetic force itself. Its value is close to 1 over 137. Feed that into Schwinger's little formula, alpha over 2 pi, and you get a number near 1,000th, almost exactly the excess that Cushon-Foley had measured. Theory and experiment shook hands on the same tiny number. This was a stunning success. The mysterious excess in the electron's magnetism was not mysterious anymore. It was the fingerprint of the electron talking to its own field, and Schwinger had computed that fingerprint from first principles and matched the measurement. Quantum electrodynamics was not just a tidy story. It gave the right number. Schwinger shared the Nobel Prize in 1965 with Richard Feynman and the Japanese physicist Shinichiro Tomonaga, who had reached similar results independently, even while working in the wreckage of post-war Japan. Feynman gave the theory its famous pictures, little diagrams of particles meeting and parting that made the endless self-interactions possible to organize and count. But the first correction, the leading term, belonged to Schwinger's simple formula. He was proud of it to the end. When Julian Schwinger died, the formula alpha over 2 pi was carved onto his tombstone, a single line of mathematics standing for a life's work. It is hard to imagine a quieter monument, or a more confident one, so the picture had grown. Dirac gave the sharp value of 2. Schwinger explained the first correction on top of it, the electron's endless exchange of photons with itself adding about 1,000th, and that correction was only the beginning, the first and largest of an unending series of ever smaller terms. But before we follow that series deeper, we have to face the strange thing Schwinger's calculation quietly assumed. For the electron to constantly toss and catch photons, empty space cannot really be empty. It has to be a place where things are always happening, even when nothing is there. Think about what we usually mean by empty space. Take a sealed box, pump out all the air, cool it to the lowest temperature nature allows, shield it from every outside field, and remove every particle you can find. What remains, you would think, is nothing at all, a perfect void, still and dead. For centuries, that is exactly what a vacuum was taken to be. Quantum physics says otherwise, and the electron's magnetism is one of the reasons we believe it. In the modern picture, built by Schwinger, Feynman, Tomonaga and others, the universe is filled everywhere with fields. There is an electron field, a photon field, a field for every kind of particle, all overlapping and filling all of space. A particle is just a ripple, a concentrated disturbance in its field. Where the field is calm, there is no particle, but a quantum field is never perfectly calm. The reason is a rule discovered by Werner Heisenberg, the uncertainty principle. It says, among other things, that you cannot pin down both the energy of a region and the exact moment together with perfect sharpness. Over very short spans of time, the energy of even empty space is allowed to flicker, and where energy can flicker, particles can briefly appear. A pair, a particle and its antiparticle, can bubble up out of nothing, exist for the tiniest instant, and vanish again before the universe can quite notice. These fleeting pairs are called virtual particles. They are not quite real in the ordinary sense because they never last long enough to be caught directly. But they are not fiction either. They are borrowings of energy, allowed and then repaid so quickly that the books always balance. Picture the surface of a pond that looks flat and calm. Look closer, and it is never truly still. Tiny bubbles rise and pop, ripples cross and cancel, a faint restless shimmer runs across the whole surface. The quantum vacuum is like that. What we call empty is a quiet, ceaseless froth. Now the electron's constant tossing and catching of photons makes sense. The electron sits in this froth, and it dresses itself in a haze of virtual photons and virtual pairs that flicker around it. That haze changes how it responds to a magnetic field. The excess magnetism Schwinger calculated is, in the end, the electron feeling the froth of the vacuum around it. The anomaly, G-2, is a direct measurement of the vacuum's activity. You might reasonably ask whether any of this can be seen apart from the G factor, whether the restless vacuum shows up anywhere else. It does. In the year 1948, the Dutch physicist Hendrik Casimir predicted that 2 flat metal plates placed extremely close together in a vacuum would feel a faint attractive force, simply because the froth of virtual activity is a little different between them than outside. the plates get gently pushed together by the vacuum itself. Decades later, that tiny force was measured, exactly as predicted. The Lamb shift that Willis Lamb found in hydrogen has the same origin. Empty space leaves fingerprints in more than one place, and they all agree. So the vacuum is not a stage on which particles act. It is a participant. It presses on plates, it shifts atomic energies, and it adds a measurable sliver to the magnetism of every charged particle. This is one of the deepest and strangest lessons of modern physics, and it is worth carrying with you. Nothing, in the physicist's sense, is doing something all the time. For the electron, that something has been measured and calculated to a precision that beggars belief, digit after digit, and the two match. Before we turn to the muon, we should look at just how perfect that match is, because it is the finest agreement between human theory and physical reality that has ever been achieved, and it is the yardstick against which every crack must be judged. To measure the electron's magnetism to its very last visible digit, you need to hold a single electron still and watch it for a long time. That sounds impossible, since electrons repel each other and never sit quietly. But over the last half-century, experimenters learned to do exactly that. They built traps, cages made of carefully shaped electric and magnetic fields that can hold one lone electron in place for months. The master of this craft was Hans Damelt, who trapped single particles and shared the Nobel Prize in 1989 for it, and after him Gerald Gabriels, who refined the method to an extraordinary degree, first at Harvard and later at Northwestern University. In their apparatus, a single electron circles in a magnetic field inside a tiny cold cavity, and its spin flips can be counted one by one. From the rhythm of those flips, they read the G-factor of the electron directly. The precision is hard to take in. The electron's G-factor is now known to about 12 digits past the decimal point. To picture what that means, imagine measuring the distance from New York to Los Angeles, and being certain of it down to the width of a single human hair. That is roughly the sharpness we have on the electron's magnetism. It is among the most precisely measured quantities in the history of science. The theory had to keep pace, and it did. Schwinger's first term, alpha over 2 pi, is only the leading piece. Beyond it lies an endless series of smaller corrections, the electron tossing and catching 2 photons, then 3, then 4, each involving more virtual particles and more ways for them to interact. Each new layer is drawn as a set of Feynman's diagrams, and each diagram stands for a specific calculation. The number of diagrams explodes as you go deeper. The 4-photon level alone involves nearly 1,000 of them. For decades, the physicist Toichiro Kinoshita, working in the United States, led the heroic effort to compute these layers, eventually reaching the level of 5 photons and many thousands of diagrams with the help of collaborators and enormous computer time. When all the layers are added, quantum electrodynamics produces a predicted value for the electron's G-factor that stretches to 12 digits. And here is the payoff. The measured value and the calculated value agree, digit for digit, to about 1 part in a trillion. Nothing else in all of science matches this. No other theory has ever been confirmed to so many decimal places. When people say the modern picture of particles rests on solid ground, this is the bedrock they mean. The electron's magnetism is the crown jewel of precision physics, the place where human calculation and physical reality meet most exactly. That agreement is so tight that physicists now run the logic in reverse. Instead of using the fine structure constant to predict the G-factor, they use the beautifully measured G-factor to determine the fine structure constant itself, extracting the strength of the electromagnetic force from the wobble of a single trapped electron. The tool has become so sharp it defines the very constant it once merely used. So for the electron, the story seems closed and triumphant. Theory and experiment shake hands to 12 digits. There is no crack here, no gap, no room for anything unknown to hide. If the whole tale ended with the electron, we would simply admire it and move on. confident that quantum electrodynamics describes the magnetism of charged particles perfectly. But the electron is only the lightest of its kind. It has heavier siblings, cousins that behave almost identically yet carry far more mass, and mass, it turns out, changes what a particle can feel. One of these cousins is more sensitive to the deep froth of the vacuum than the electron could ever be. It arrived unannounced, out of the sky, and when it did, one of the great physicists of the age reacted not with wonder but with a puzzled complaint. In the 1930s, before anyone could build a machine to make new particles, the only source of high-energy particles was the sky. Cosmic rays, streams of fast particles from deep space, rain down on the Earth constantly, and when they smash into the upper atmosphere, they shatter into showers of new particles that sleet down to the ground. Physicists carried their detectors up mountains and into deep mines to catch them. The detector of choice was the cloud chamber, a sealed box of cold, moist vapour. When a charged particle races through, it leaves a thin trail of droplets behind it, like the vapour trail of a high jet, and a magnetic field bends the trail. From how sharply the track curves, you can read the particle's mass and charge. It is a way of seeing the invisible by the wake it leaves. In the year 1936, at the California Institute of Technology, Carl Anderson, the same man who had found the positron, was studying cosmic ray tracks with his student Seth Neddermeyer. They kept finding a track that made no sense. It curved too gently to be a light electron, yet too sharply to be a heavy proton. Its mass sat squarely in between, around 200 times the electron's mass. It was a particle no one had ordered, and no theory had asked for. At first, there was hope that this middleweight particle was something predicted a few years earlier by the Japanese physicist Hideki Yukawa, a particle meant to glue the atomic nucleus together. But careful study showed it did not behave the way Yukawa's particle should. It barely interacted with nuclei at all. It was not the nuclear glue, it was simply a heavier copy of the electron, with the same charge and the same spin, just much more massive. Today we call it the muon. The story goes that when the physicist Isidore Rabi heard that this needless heavy electron existed, he said with some exasperation, "Who ordered that?" The line stuck because it captured the mood exactly. The muon did not fill a gap. It did not answer a question anyone had asked. It just appeared, an extra, a heavier twin of a particle we already understood, and no one knew why nature would bother to make it. The muon is a lepton, meaning it belongs to the same family as the electron, the family of particles that do not feel the strong nuclear force. It carries the same negative charge as the electron and the same spin of 1/2. In almost every way, it is an electron wearing extra weight. That weight is considerable. The muon is about 207 times as massive as the electron, so where an electron is a feather, a muon is more like a small stone. There is a price for that mass. The muon is unstable. Left to itself, it survives only about 2/millionths of a second before it decays, breaking apart into an electron and two ghostly, nearly massless particles called neutrinos. 2/millionths of a second sounds like no time at all, and by human reckoning it is not. But for a particle physics experiment, it is a long and useful life, long enough, as we will see, to send a muon racing around a magnetic ring thousands of times before it disappears. So nature, for reasons still not fully understood, made 3 copies of the electron at 3 different weights. The electron is the lightest, the muon is the middle one, heavier and short-lived. There is even a third, the tau, heavier still. They are like the same note played in 3 octaves. The question Rabi asked in frustration is, in a sense, still open. But for our story, the muon's extra weight is not a nuisance. It is the whole point, because that heaviness makes the muon feel things the electron cannot. We ended with a claim that needs unpacking. The muon's extra weight lets it feel things the electron cannot. To see why, we have to return to the froth of the vacuum and think carefully about who a particle can meet there. Recall that any charged particle sits in a haze of virtual particles flickering in and out of existence around it. The electron's anomaly, its excess magnetism, comes from this haze. The muon has its own haze, and because the muon carries the same charge and spin as the electron, most of its haze looks the same. The virtual photons, the virtual electron pairs, all contribute in nearly the same way. To a first approximation, the muon's magnetism follows the very same rules as the electrons, Schwinger's term and all. But the vacuum can contain more than the light familiar particles. In principle, it can flicker with heavy particles too, ones far more massive than the electron, including particles we have never directly seen. Whether such a heavy visitor makes a real difference to a given particle depends on a competition between two masses, the mass of the particle we are watching and the mass of the heavy visitor flickering nearby. Here is the rule, in plain terms: a particle's sensitivity to a heavy virtual visitor grows with the square of the particle's own mass. Double the mass of the particle you're watching, and its sensitivity to heavy unknown things goes up fourfold. The muon is about 207 times heavier than the electron. Square that number, and you get close to 43,000. So the muon is roughly 43,000 times more sensitive than the electron to the influence of heavy particles hiding in the vacuum. That factor changes everything. The electron is so light that heavy virtual visitors barely tug on it at all. Their effect is buried far below the 12 digits we can measure, invisible in practice. The muon, being heavier, feels those same visitors tens of thousands of times more strongly. If there is some unknown heavy particle out there, too massive to have been made in any machine, the electron will shrug it off while the muon will register a faint but real nudge in its magnetism. Think of it like two bells of different size hung in a great hall, and somewhere far off a heavy door slams. The small bell, the electron, is too stiff and light to answer such a distant low sound. The larger bell, the muon, has just enough mass to catch it, and it hums very faintly, at a pitch the small bell never picks up. The muon is the better listener for heavy hidden things. This is why the muon, not the electron, is the crack we care about. The electron's magnetism is a perfect check on the light, well-known physics, and it passes that check to 12 digits. The muon's magnetism includes everything the electron's does, plus a far stronger sensitivity to whatever heavy particles might exist beyond our current list. If our list of particles is complete, the muon's measured magnetism should match the calculated value exactly, just as the electron's does. If our list is missing something heavy, the muon is where the discrepancy will first show itself, so the plan almost writes itself. Measure the muon's magnetism as precisely as possible. Calculate what it should be, using only the known particles, then compare. If the two agree, our picture of matter holds. If they disagree, by an amount too large to explain away, then something is tugging on the muon that is not in our theory, and that something would be a genuine new piece of the universe. But to run that plan, we first need to be clear about what the calculation includes, about what the known list of particles actually is. That list has a name and a shape, and it is one of the great achievements of the last century. The known list of particles has a formal name, the Standard Model of Particle Physics, and it deserves that grand title. It is the distilled result of a century of experiment and theory, and it describes every particle we have ever directly detected and 3 of the 4 forces that act between them. When physicists talk about the theory the muon might break, this is the theory they mean. At its heart, the Standard Model sorts the building blocks of matter into 2 families. The first family is the quarks, and there are 6 of them, given playful names: up and down, charm and strange, top and bottom. Quarks are the pieces inside protons and neutrons. A proton, for instance, is 2 up quarks and 1 down quark bound tightly together. Quarks never travel alone. They are always locked inside larger particles by the strong force. The second family is the leptons, and there are 6 of these as well. 3 carry electric charge, the electron and its 2 heavier cousins we have already met, the muon and the tau. The other 3 are the neutrinos, 1 paired with each charged lepton, particles so light and so aloof that trillions pass through your body every second without touching a thing. Quarks and leptons together, 12 particles in all, make up matter. Then there are the forces, and in this theory the forces are carried by particles too. Electromagnetism, the force behind light, and magnetism and chemistry, is carried by the photon, the particle of light itself. The strong force, which glues quarks together and holds the nucleus, is carried by particles called gluons. The weak force, which drives certain kinds of radioactive decay and lets the muon fall apart, is carried by 3 heavy particles named the W+, the W-, and the Z. Each force is a game of catch, particles of matter tossing force carriers back and forth. One more piece completes the picture, and it took the longest to find. In the year 2012, at the Large Hadron Collider at CERN near Geneva, thousands of physicists confirmed the existence of the Higgs boson, the particle tied to the field that gives the others their mass. The theory had predicted it nearly 50 years earlier, from the work of Peter Higgs and François Englert and others, and its discovery was the last major prediction of the Standard Model to come true. Higgs and Englert shared the Nobel Prize the following year. The Standard Model came together over the 1960s and 70s, built by many hands. Sheldon Glashow, Steven Weinberg and Abdus Salam wove electromagnetism and the weak force into a single unified description, the electro-weak theory, and shared the Nobel Prize in 1979 for it. Others built the theory of the strong force. Piece by piece, a single framework emerged that could account for the whole particle zoo, and it works astonishingly well. Time after time, the Standard Model has predicted the existence and the properties of particles before they were found, and the machines then found them exactly where the theory said. It predicted the W and Z particles and their masses, and CERN found them in the early 1980s. It predicted the top quark, and Fermilab found it in 1995. The electron G2 agreement to 12 digits is a Standard Model triumph. By almost any measure, it is the most successful physical theory ever written. So when we say the muon might crack the Standard Model, we're not talking about a shaky guess. We're talking about the best tested theory in the history of science, confirmed again and again to remarkable precision. A crack in this theory would not be a small correction to a minor idea. It would be the first solid sign of a whole layer of nature that this magnificent, thoroughly checked framework does not contain. And there is good reason to think such a layer exists, because for all its success, the Standard Model is silent on some very large questions. For all its precision, the Standard Model describes a world that we know is not the whole world. It is like a beautifully detailed map that stops at a coastline, accurate everywhere it reaches, yet plainly not covering the entire globe. Several great features of the universe lie off its edges, and physicists can point to each one. Start with gravity. We feel it every second. It holds the planets in their orbits, and it is described superbly by Albert Einstein's general relativity. Yet gravity is nowhere in the Standard Model. The theory covers electromagnetism, the strong force, and the weak force, but it has no place for the fourth force, the one that shapes stars and galaxies. Nobody has yet found a way to fit gravity into the same quantum framework as the others. The map simply ends there. Then there is dark matter. When astronomers weigh galaxies by their spin and their pull on one another, they find far more mass than the visible stars and gas can account for. Something unseen, roughly 5 times as much as all ordinary matter, is holding galaxies together with its gravity. Whatever it is not made of any particle in the Standard Model. The theory has no candidate for it. 1/4 of the universe's contents is missing from the list. Alongside it sits dark energy, the name we give to whatever is driving the expansion of the universe to speed up rather than slow down. It appears to make up most of the universe's total budget, and the Standard Model says nothing about it at all. There is a subtler gap closer to home, and it involves the neutrinos. In its original form, the Standard Model assumed neutrinos were completely massless. But experiments deep underground, in Japan and in Canada, watch neutrinos change from one type into another as they travel. a shifting that is only possible if neutrinos carry a tiny sliver of mass. Takaaki Kajita and Arthur MacDonald shared the Nobel Prize in 2015 for showing it. The neutrinos have mass, small but real, and the plain standard model did not predict it. Here is a place where nature has already stepped outside the original theory. And there is the deepest puzzle of all, the reason any of us are here. When energy turns into matter, it makes matter and antimatter in equal amounts, and when they meet, they annihilate back into energy. In the hot early universe, there should have been exactly as much antimatter as matter, and they should have wiped each other out completely, leaving nothing but light. Instead, a tiny excess of matter survived, about 1 part in a billion, and everything we see is built from that leftover. The standard model, as it stands, cannot explain where that crucial imbalance came from. So the theory that predicts the electron's magnetism to 12 digits cannot tell us what most of the universe is made of, cannot include gravity, did not predict that neutrinos have mass, and cannot say why matter exists at all. These are not small footnotes, they are enormous, and they tell us plainly that the standard model, magnificent as it is a piece of a larger theory we have not yet found. That larger theory would contain new particles, new forces, or both, and if those new things exist, they must flicker in the vacuum along with everything else, which brings us back to the muon. If there is a heavier layer of physics out there, the muon's magnetism is one of the few places where its faint influence might already be reaching us, tens of thousands of times more strongly than it reaches the electron. The trouble is that new particles are usually too heavy to make directly, even in our largest machines. So we need another way to sense them, a way that does not require building them at all. That way is precision, and it is worth understanding exactly how a single careful number can reveal a particle no one has ever produced. There are 2 ways to discover a new particle, and it helps to see them side by side. The first is direct, and it is the one people picture. You build a machine that slams particles together at enormous energy, and out of that energy new particles are born, following Einstein's famous rule that energy and mass are 2 forms of the same thing. Gather enough energy in a small enough space, and heavy particles can materialize out of it. This is how the Higgs boson was found at CERN, and how the top quark was found at Fermilab. The direct way has a hard limit. To make a particle, you need at least as much energy as its mass demands, and the heavier the particle, the more energy you need. If a new particle is very heavy, heavier than any machine can reach, you cannot make it, no matter how clever your detector. It stays beyond the wall, unreachable by brute force. And there is every reason to think some of the missing physics lies far past the energies we can currently produce. The second way does not require making the particle at all. It relies on the froth of the vacuum. Remember that every particle, even one far too heavy to create directly, can still flicker briefly into existence as a virtual particle and influence things around it. It leaves a faint imprint on quantities we can measure, even though it never appears in the open. So instead of trying to make the heavy particle, you measure some ordinary quantity with extreme care, and you look for the small imprint the unseen particle leaves behind. This is the indirect way, the way of precision. It is like studying a magician's trick not by grabbing the hidden card, but by watching the tiny tell in the performer's hand. The small effect that gives away what you cannot see directly. A heavy unknown particle that can never be made in a lab still tugs, ever so slightly, on the things that can be measured, and a precise enough measurement will feel that tug. The muon's magnetism is the finest fingerprint reader we have for this purpose. Every particle that exists, known or unknown, light or crushingly heavy, contributes to the froth around the muon, and so leaves its mark on the muon's anomaly. The measured value of G-2 for the muon is, in effect, a sum over everything in nature that can flicker near it. If we calculate that sum using only the known particles of the standard model, and the answer matches the measurement, then the known particles are all there is, at least to the precision we have reached. If the calculated sum falls short of the measurement, the gap is the imprint of something we left out. That is the whole logic of the Muon G2 story, and it is worth saying plainly because it is easy to lose in the technical detail. We're not looking at the muon to learn about the muon. We're using the muon as a probe, a small sensitive instrument that samples the entire content of the vacuum and reports back a single number. The number is G-2. The report is a comparison between what we measure and what we can calculate. This is also why the precision matters so much. The imprint of a heavy new particle on the muon is tiny, buried in the 8th or 9th digit of the anomaly. To see it, both the measurement and the calculation have to be pushed to that same extraordinary depth, and they have to be trusted there. A crack only counts if the two sides are each sharp enough that the gap between them cannot be a mistake, so everything now turns on measurement. We have the logic, we have the reason the muon is the right probe, and we know what we are comparing against. What remains is the hardest, most beautiful part of the experiment, the trick of catching a muon, setting it spinning, and reading its faint magnetism before it decays. To measure the muon's magnetism, you have to watch it spin, and the trick physicists use is beautiful in its simplicity. It rests on the same behaviour you can see in a child's spinning top. Set a top spinning and tilt it, and it does not just fall over. Its axis sweeps slowly around in a cone, a stately circling motion called precession. A spinning magnet in a magnetic field does the same thing. Its spin axis precesses, wheeling around the direction of the field at a steady rate. The muon is a spinning magnet, so when you place it in a magnetic field, its spin precesses. The rate of that precession depends directly on its magnetism, on its G-factor. Measure how fast the muon spin wheels around, measure the strength of the field it sits in, and you can extract the muon's magnetic moment. That is the whole idea. Everything else is the art of doing it cleanly. The setup is a ring. Muons are injected into a large circular pipe held inside a powerful, carefully uniform magnetic field, and they race around the ring at nearly the speed of light. As they circle, two things rotate. The muon's direction of motion swings around the ring once per lap, and the muon's spin axis precesses at its own rate. If the G-factor were exactly 2, these two rotations would keep perfect step, the spin turning exactly as fast as the motion. Because the G-factor is a little more than 2, the spin creeps ahead of the motion, gaining a little each lap. That slow creep, the gap between how fast the spin turns and how fast the muon's motion turns, is called the anomalous precession. And here is the elegant part. The anomalous precession does not depend on the full G-factor. It depends only on the excess, on G-2 itself. The experiment measures the very quantity we care about directly, as a slow drift you can time. The muon quietly announces its anomaly by how far its spin runs ahead of its path. Two lucky facts make this possible. The first is that muons are born already aligned. When muons are produced from the decay of other particles called pions, they come out with their spins pointing in a known direction, so you do not have to line them up yourself. The second is that muons announce which way their spin is pointing when they die. When a muon decays, it throws out its electron preferentially in the direction its spin was facing. By catching those electrons and noting which way they fly, and when, experimenters can read the muon's spin direction at the moment of decay without ever touching the muon itself. There is a final gift, and it comes from Einstein. A muon at rest lives only about 2/millionths of a second, far too short to circle a ring many times. But these muons are moving at nearly light speed, and relativity says that fast-moving clocks run slow. From our point of view, the racing muon's internal clock is stretched, and it survives many times longer than a resting muon would. Long enough to loop the ring hundreds of times before it decays. Time dilation, the same effect that keeps cosmic ray muons alive long enough to reach the ground, gives the experiment the time it needs, so the method comes together. Fill a ring with spinning aligned muons, let them race until they decay, catch their farewell electrons and time them, and watch the count rise and fall as the muon spins wheel around, again and again. From the rhythm of that rise and fall, read the anomalous precession. From the precession and the field, read G-2. It is a way of hearing a particle's magnetism in the ticking of its own decay. This is not a new idea. It was first carried out more than half a century ago, not in America but in Europe, at the laboratory that would come to define particle physics, where the technique was invented and slowly perfected across 3 generations of experiments. The place was CERN, the great European laboratory near Geneva, Switzerland, founded in the years after the Second World War to give Europe a shared home for physics. In the late 1950s, physicists there set out to measure the muon's magnetism using the precession method, and in doing so they built the first of the Muon G2 experiments. Over the next 2 decades, CERN would run 3 of them, each sharper than the last. The first CERN experiment, running around 1959, was modest by later standards, but groundbreaking in its aim. It sent muons through a long magnet and measured their precession well enough to confirm that the muon, like the electron, has an anomaly close to Schwinger's value of alpha over 2 pi. This mattered a great deal. It showed that the muon really is a heavy copy of the electron in its magnetism, obeying the same quantum electrodynamics, tossing and catching the same virtual photons. The muon's G-factor was a little above 2, just as the theory required. The second CERN experiment in the 1960s introduced the storage ring, the circular design that all later experiments would use. Instead of a straight magnet, muons now circled inside a ring, precessing as they went, which let them be watched for far longer and measured far more precisely. The anomaly was pinned down to better than 1 part in 1,000 of itself, a real leap. The third CERN experiment, running into the 1970s and led by the Italian physicist Emilio Picasso among others, pushed the precision further still, to a few parts in a million. At that depth, the measurement was no longer testing just Schwinger's first term. It was sensitive to the smaller, higher-order pieces, the muon tossing and catching several photons, and even to the first faint contributions of the strong and weak forces to the muon's magnetism. The measured anomaly and the calculated one still agreed, and each new digit of agreement was a fresh confirmation of the whole framework. These early experiments did something quietly essential. They proved the method worked, and they proved the muon behaved. Through the 1970s, the muon's magnetism was measured and calculated in step, with no crack between them. The standard model, still being assembled in those very years, passed the muon test at the precision then available. Nothing seemed amiss. But the CERN experiments also revealed the coming challenge. As precision improved, the calculation had to include not just the clean electromagnetic effects, but the messier contribution of the strong force, the force that binds quarks. That contribution was small, but it was the hardest part of the theory to compute, and everyone could see that at some point it would become the limiting factor. The measurement was racing ahead. The theory would have to keep up, and its weakest link was the strong force. By the end of the third experiment around 1977, CERN had taken the muon anomaly about as far as its machines could reach. The result was a landmark, a beautiful confirmation of quantum electrodynamics applied to the muon, and it left the field with a clear next step. To go deeper, to reach the digits where a truly heavy new particle might leave its mark, someone would need a bigger, colder, more perfect ring and a far more intense supply of muons. The baton passed across the Atlantic. In the United States, at Brookhaven National Laboratory on Long Island, physicists took up the challenge and built exactly that, a giant superconducting storage ring designed to measure the muon's magnetism more precisely than anyone ever had. Their experiment would run through the 1990s and into the new century, and when its results came in, they would not simply confirm the theory. For the first time, the measured number and the calculated number would fail to line up, by an amount just large enough to make people lean in and look harder. Brookhaven National Laboratory sits on Long Island in New York, and in the 1990s it became the home of the most precise muon experiment yet attempted, led by the physicist Vernon Hughes, who drove the project with famous determination. The goal was to measure the muon's anomaly several times more precisely than CERN had, sharp enough to test not just the electromagnetic and strong contributions but the tiny effects of the weak force, and sharp enough to feel any hint of physics beyond the known list. The heart of the experiment was a storage ring of extraordinary size and quality, about 15 meters across, roughly the width of a 4-lane road, wound with superconducting wire and cooled until it could hold a strong, breathtakingly uniform magnetic field. The field strength was close to 1.5 Tesla, tens of thousands of times the Earth's, and it had to be even across the whole ring to a few parts in a million, because any unevenness would blur the precession the experiment was trying to time. Building a magnet that large and that uniform was itself a years-long feat. Into this ring the experimenters fired muons, aligned and ready, and let them race and precess and decay, catching the farewell electrons in detectors around the ring and timing the rise and fall of their count. From that rhythm they extracted the anomalous precession, and from it the muon's anomaly, digit by careful digit. By the time the experiment finished its runs, around the year 2001, it had measured G-2 for the muon to better than 1 part in a million, sharper than any measurement before it. Then came the comparison with theory, and this is where the whisper began. The standard model prediction for the muon anomaly was itself a huge collaborative calculation, summing the electromagnetic strong and weak contributions. When the Brookhaven measurement was set beside that predicted value, the two did not quite match. The measured anomaly sat a little above the calculated one. The gap was small in the 8th digit of the number, but it was there, and it did not go away as the analysis was refined. How seriously to take a small gap depends on how it compares to the uncertainty on each side, and physicists measure that in units called standard deviations, or sigma. A gap of 1 sigma is noise, easily a fluke. The Brookhaven gap grew, as the numbers were finalised, to around 3 sigma. 3 sigma means the odds of such a gap appearing by pure chance are only a few in 1,000. That is not proof. In particle physics, 3 sigma is a hint, not a discovery. But it is exactly the kind of hint that makes a field sit up. What made it tantalising was the muon's nature. We already knew the muon is the sensitive probe, tens of thousands of times more responsive than the electron to heavy hidden particles. A gap in the muon's magnetism, with the measurement sitting above the prediction, is exactly the shape you would expect if some unknown heavy particle were flickering in the muon's vacuum haze, adding a little extra magnetism the standard model calculation did not include. The Brookhaven result was not proof of new physics, but it looked, unmistakably, like the kind of clue new physics would leave. The trouble was that a 3 sigma hint can be many things. It can be a real crack. It can be an underestimated uncertainty on the measurement. It can be a mistake somewhere in the enormous theoretical calculation, especially in its hardest part, the strong force contribution that had worried people since the CERN days. 3 sigma is precisely the region where honest physicists disagree about what they're seeing. So Brookhaven left the field with a genuine puzzle and a clear mandate. Measure it again, better. Pin the number down until the hint either sharpened into a discovery or faded into nothing. But before a new experiment could do that, it is worth looking closely at the number itself because its anatomy tells you exactly where the crack could be hiding. Let us lay the muon's anomaly out in the open and see what it is made of, because the shape of the number is the map of the whole search. The muon's anomaly, G-2 divided by 2, is a small decimal that begins 0.0011659 and then continues into further digits that are the real battleground. Almost all of that number is understood. The fight is over the last few digits. Start at the top. The largest single piece by far is Schwinger's term, the muon tossing and catching 1 photon, equal to the fine structure constant divided by 2 pi. That one term, about 1,000th, accounts for the great bulk of the anomaly. The muon, like the electron, gets most of its excess magnetism from this simplest interaction with its own field. If you knew only Schwinger's term, you would already have the Muon's anomaly almost right. Below that come the higher order electromagnetic terms, the muon tossing and catching 2 photons, then 3, then 4, each smaller than the last, each drawn as more of Feynman's diagrams and computed with great care. These purely electromagnetic contributions are known to extraordinary precision, the same quantum electrodynamics that nails the electron to 12 digits. This part of the muon's number is not in doubt, it is solid ground. Then come the 2 harder families of contributions, smaller in size but far larger in trouble. The first is the effect of the weak force, the force carried by the heavy W and Z particles that also lets the muon decay. Because those force carriers are so heavy, their contribution to the muon's magnetism is tiny, but it can be calculated cleanly and it is well understood. The weak part is small and known. The second harder family is the real problem, and it deserves its own name. It is the contribution of the strong force, the force that binds quarks, entering through virtual particles made of quarks flickering in the muon's haze. This is called the hadronic contribution, hadron being the general word for particles built from quarks, like the proton. The hadronic contribution is only about 60 parts in a million of the whole anomaly, a small slice. But it is by far the hardest slice to calculate, because the strong force does not yield to the neat step-by-step methods that work so well for electromagnetism. Here is the crucial fact. The uncertainty on the entire muon anomaly, the fuzziness that decides whether a crack is real, comes almost entirely from this one hadronic slice. The electromagnetic part is sharp, the weak part is sharp, but the strong force part is blurry, and its blur sets the limit on the whole prediction. When the Brookhaven measurement sat above the predicted value by 3 sigma, the size of that sigma was governed mostly by how well anyone could compute the hadronic contribution. So the anatomy of the number points like an arrow. The gap between measurement and theory lives in the last few digits. The measurement side of those digits can be sharpened by a better experiment. The theory side of those digits is dominated by the strong force contribution, the one piece that resists calculation. Whether the crack is a true sign of new physics or an artifact of an imperfect calculation depends, more than anything, on getting that hadronic slice right. That is the state the field was left in after Brookhaven. A tempting 3 sigma gap, sitting in the strong force limited digits of the muon's anomaly, begging to be tested more sharply from both sides. The measurement needed to improve, and to improve it, the physicists decided not to build a new ring, but to reuse the Brookhaven one, the great 15-meter superconducting magnet already built and tuned. There was only one difficulty. The best place to run the new experiment was not on Long Island. It was outside Chicago, more than 3,000 miles away, and the enormous, delicate ring would somehow have to be moved there in one piece. Picture a wide, flat truck rolling down an empty highway in the dark, moving at little more than a walking pace, with police lights ahead and behind. On its bed sits a single white ring 50 feet across, wrapped and braced, wider than the road has any right to carry. People stand along the shoulder to watch it pass, because there is nothing else on Earth quite like it. This was the summer of the year 2013, and the great Brookhaven storage ring was being moved to Illinois. The reason for the move was money and time. Building a new ring of that size and quality would have cost tens of millions of dollars and years of work. The Brookhaven ring already existed, already tuned to hold a beautifully uniform field. Fermilab, outside Chicago, could make a far more intense and pure beam of muons to fill it. So the plan was to marry the two, Brookhaven's magnet and Fermilab's beam, which meant carrying the magnet more than 3,000 miles across the country. The trouble was that the ring could not bend. Its superconducting coils were set in a single circular frame, and if that frame flexed by more than a small fraction of an inch, the coils inside could be damaged beyond repair. A structure 50 feet wide had to be moved thousands of miles without ever twisting or sagging past that hair's width limit. It was like carrying a full pane of antique glass across a continent, except the glass was the size of a house. They chose to go the long way, mostly by water, because water is smooth. The ring was sealed against the weather and floated onto a barge. It travelled south down the Atlantic coast, around the tip of Florida, into the Gulf of Mexico, then up through a chain of rivers and inland waterways toward Illinois. Water carried it gently for most of the journey, thousands of miles of slow, careful floating, the ring riding the current the way a leaf rides a stream. Only the ends of the trip went by road, and those were the tense parts. A special truck built to carry the ring level and steady moved it overland at night, when the highways were empty, creeping along at a crawl so no bump could jolt the frame. Sensors watched the structure constantly for any sign of strain. The overland legs took days to cover distances a car would manage in hours. The whole journey ran about 35 days and covered roughly 3,200 miles, and along the way it became a small public event. Fermilab shared the route, and crowds gathered to see the strange glowing ring pass through their towns in the middle of the night. A machine built to measure the magnetism of a particle 200 times lighter than a proton had become, for a few weeks, a thing that ordinary people drove out to witness. There is something fitting in that. A piece of the invisible made briefly, physically visible. When the ring reached Fermilab, it arrived intact, the coils unharmed, the frame within its tolerance. Then came the slow work of settling it into its new home, powering it up and coaxing its field back to the flawless uniformity the measurement demanded, shimming the magnet, adjusting it piece by piece until the field was even to a few parts in a million across the whole ring, took the better part of a year on its own. By the middle of the decade, the ring was alive again, cold and humming, its field smoothed and ready, waiting for muons. The great magnet that had first found a whisper of a crack on Long Island now stood outside Chicago, aimed at the same question with a sharper beam and better detectors. What remained was to fill it with spinning muons, and this time read their farewell with enough care to turn a whisper into either a shout or a silence. The Fermilab experiment works on the same principle the CERN and Brookhaven experiments used, the slow creep of a muon's spin running ahead of its motion. But everything around that principle was pushed to a new level of care. It begins with the beam. Fermilab takes a stream of protons, slams them into a target to make particles called pions, and lets those pions decay into muons that are born already spin-aligned. By the time the muons reach the ring, they are a clean, pure bunch, all pointing the same way, with far less contamination than earlier experiments had to fight. The muons are injected into the ring and steered so they circle inside the pipe, without drifting into the walls. Keeping them on course takes more than the main magnetic field. The field alone would let them wander up and down, so the experiment adds a set of electric plates, called quadrupoles, that gently focus the beam and hold it in a tight orbit. This is a subtle business, because those focusing fields could disturb the very precession being measured, so their effect has to be understood and corrected with great precision. Then the muons race, hundreds of laps each, precessing as they go, until they decay. When a muon dies, it throws out an electron, and that electron carries the news of which way the muon's spin was pointing at that instant. Around the inside of the ring sit 24 detectors, blocks of a special crystal that flash with light when an electron strikes them. Each flash is caught, timed, and measured for its energy. The stream of flashes, rising and falling in a slow rhythm, is the raw signal of the whole experiment. The rhythm is the key. As the muon spins wheel around, the electrons come out preferentially in one direction, so the count of high-energy electrons reaching the detectors swells and shrinks, in time with the anomalous precession. Plot the count against time and you see a gentle wave riding on a falling curve, the falling curve being the muon steadily decaying away, the wave being the spin creeping around. The frequency of that wave is G-2, laid bare. To turn frequency into a magnetic moment, you also need to know the field with exquisite precision, and here the experiment uses a trick of great elegance. It measures the field not in ordinary units, but by comparing it to the magnetism of the proton, using probes that read the field through the behaviour of protons in water. Small trolleys of these probes are sent around the ring to map the field everywhere, over and over, so the exact field each muon feels is known across the whole orbit. Two quantities, then, are measured with extreme care. One is the muon's anomalous precession frequency, the wave in the electron count. The other is the magnetic field, read through the proton. The ratio of those two numbers gives the muon's anomaly, cleanly, with the messy details of the apparatus dividing out. It is a beautiful piece of design, turning a fantastically hard measurement into the comparison of two frequencies. Everything is done blind, on purpose. To keep hope from tilting the answer, the analysis teams work with the clock deliberately offset by a secret amount, so no one knows the true result until the very end, when the offset is revealed and the number is unblinded all at once. This guards against the human tendency to stop looking for errors once the answer looks pleasing. Only when every check is done is the envelope opened. By the year 2021, the first batch of Fermilab data was analysed, checked, and ready to unblind. The ring had run, the muons had spun, the flashes had been counted and timed. The field had been mapped. The moment had come to see whether the Brookhaven whisper would grow. On the 7th of April, in the year 2021, the Fermilab collaboration announced its first result, and the number landed almost exactly where Brookhaven's had. The muon's measured anomaly again sat above the standard model prediction that the theory community had settled on the year before. 2 experiments, on 2 continents, decades apart, using the same great ring in 2 homes, had found the muon a little more magnetic than the theory said it should be. The whisper had not gone away. It had been echoed. That echo mattered enormously. A lone result, however careful, always carries the worry that some quiet flaw in that one experiment produced it. But Fermilab's measurement was independent in its beam, its detectors, its analysis teams, and its era, and it agreed with Brookhaven closely. When you combine 2 independent measurements that agree, the uncertainty shrinks and the result grows firmer. The combined muon measurement now stood on much stronger legs than either experiment alone. When the combined measurement was set against the agreed prediction, the gap reached about 4.2 sigma. Recall what sigma means. 1 sigma is noise. 3 sigma, the Brookhaven level, is a hint worth chasing. 5 sigma is the traditional line for claiming a discovery, the point where the odds of a chance fluke fall to about 1 in 3.5 million. 4.2 sigma sits tantalizingly between the hint and the discovery, close enough to make the whole field lean forward, not quite far enough to celebrate. The announcement drew the kind of attention physics rarely gets. Here was a possible first solid sign of physics beyond the standard model, exactly where theory said a heavy hidden particle would leave its mark, in the magnetism of the sensitive muon. If the gap were real, it would mean the sea of virtual particles around the muon contained something not on our list, something new. It would be the crack the title promises, a genuine fissure in the best-tested theory ever written. The mood was electric but disciplined. The experimenters were careful to say what 4.2 sigma is and is not. It is strong evidence that the measured number differs from that particular prediction. It is not, on its own, proof of new particles, because a gap between measurement and prediction can come from either side. The measurement was now very solid and about to get more so. The question was whether the prediction on the other side of the gap was equally solid, and that was the quiet catch inside the celebration. The 4.2 sigma gap was measured against one specific value of the standard model prediction, the value the Theory Initiative had published in the year 2020 after long collaborative effort. That prediction rested, as all such predictions must, on the hardest piece of the calculation, the strong force contribution. If that piece were even slightly off, the size of the gap and the number of sigma could change. So the year 2021 left physics in a strange and thrilling suspense. The measurement had been confirmed and sharpened. 2 great experiments agreed. the muon really did appear more magnetic than the leading prediction, at a level just short of discovery. Whether this was the long-awaited crack in the standard model, or a subtle miscalculation of the standard model's own value, now depended entirely on the theory side of the ledger, on whether the predicted number could be trusted to the same depth as the measured one. To judge that, we have to cross over to the theorist's side and watch how they build the prediction, because the drama was about to move from the experiment hall to the calculation itself. The measured number now had to be compared to a calculated one, and building that calculated number is a labour as vast in its own way as building the ring. The standard model prediction for the muon's anomaly is not a single formula. It is a towering sum of contributions, thousands of separate pieces, each corresponding to a different way the muon can interact with the froth of the vacuum, and each computed as carefully as human effort allows. The pieces sort into the same families we met when we took the number apart. First, the electromagnetic contributions, the muon exchanging photons with itself, 1, 2, 3, 4, even 5 at a time. These are computed with the same quantum electrodynamics that pins the electron to 12 digits, and they are known with breathtaking precision. Toichiro Kinoshita and his collaborators spent decades grinding through the tens of thousands of diagrams involved. This part of the prediction is rock solid. Second, the weak contribution, the muon feeling the heavy W and Z particles. Because those carriers are so massive, their effect is tiny, but it can be calculated cleanly, and it too is well understood and firmly nailed down. Between them, the electromagnetic and weak pieces make up nearly the entire number, and nearly all of it with tiny, trustworthy uncertainty. Then comes the third family, small in size but overwhelming in difficulty, and it is where all the trouble lives. This is the hadronic contribution, the muon-feeling virtual particles made of quarks, particles that flicker in and out under the rule of the strong force. It amounts to only about 60 parts in a million of the whole anomaly, a thin slice. But its uncertainty dwarfs that of every other piece combined. The blur on the entire prediction comes almost entirely from this one slice. There is a reason the strong force resists calculation. For electromagnetism, the interactions are weak enough that you can compute the largest effect, then a smaller correction, then a smaller one still, each term shrinking neatly so the series settles down. The strong force does not cooperate. It is so powerful up close that the corrections do not shrink. They can be as large as the thing you started with. The tidy method of adding ever smaller terms simply fails. You cannot compute the strong force contribution the way you compute the electromagnetic one. So theorists need another route entirely to get the hadronic slice, and over the years 2 very different routes emerged. Both aim at the same number, both are legitimate, and in recent years they have not agreed with each other, which is the twist that turned the whole story on its head. The first route sidesteps the calculation by using real measurements from other experiments as a stand-in. The second route confronts the strong force head-on, simulating it directly on enormous computers. For a long time, only the first route was precise enough to use, and it was the first route that produced the prediction against which the 4.2 sigma gap was measured. Understanding that gap, and what has happened to it since, means understanding both routes, starting with the one built from real collision data. Everything now depends on this hadronic slice, the small, stubborn piece where the strong force refuses to be tamed by ordinary calculation. If the experimenters gave us the sharpest measurement, the theorist's whole challenge is to match it in this one slice. So it is worth slowing down and looking closely at exactly why the strong force is so hard, and what the 2 rival methods actually do. The strong force is the force that holds quarks together inside protons and neutrons, and it is aptly named. It is the most powerful of the forces at short range, so powerful that quarks can never be pulled apart into freedom. Try to separate 2 quarks, and the force between them does not fade with distance the way gravity or electromagnetism does. It stays strong, and the energy you pour in eventually conjures new quarks out of the vacuum, so you never get a lone quark, only new bound particles. Quarks live in permanent confinement. This ferocious strength is exactly what makes the hadronic contribution to the muon's magnetism so hard to compute. In the muon's vacuum haze, a virtual photon can briefly turn into a flickering cloud of quarks and antiquarks bound by the strong force, and then turn back. This process, a virtual photon becoming a churn of quarks for an instant, is called hadronic vacuum polarization, and it is the single largest source of uncertainty in the entire prediction. The name is a mouthful, so hold it by its meaning: the strong force's contribution to the froth around the muon. The reason it resists calculation goes back to that ferocious strength. For a weak force, you can compute the main effect and then add smaller and smaller corrections that trail off politely. For the strong force, the corrections do not trail off. Near the quarks, the force is so strong that each correction can be as big as the last, and the neat series that works so beautifully for electromagnetism simply refuses to converge. The standard tool of the trade breaks in your hands. Picture trying to predict the path of a leaf. In a gentle breeze you can do it, estimating the main push of the wind and then small gusts as corrections. But drop the leaf into a roaring rapid, where the water is as turbulent as it is fast, and the method collapses. Each swirl is as strong as the current itself, and no amount of small corrections will tame it. The strong force, up close, is the rapid, not the breeze. Because the direct calculation fails, physicists cannot simply write down the hadronic vacuum polarization from the theory alone, at least not by the ordinary method. This one term, tiny as it is, holds the fate of the whole comparison. Its uncertainty sets the size of sigma. Whether the muon's gap is 4 sigma or 2 sigma or 0 depends, more than anything else, on the value of this stubborn slice and on how confidently it can be pinned down. So the field faced a hard fork. To get the hadronic contribution, you either find a clever way around the broken calculation, using real experimental data as a substitute, or you find a way to compute the strong force numerically that does not rely on the failed series at all. Both paths were attempted. For decades, the first path, the data-driven one, was the only one precise enough to trust, and it gave the prediction that made the muon's gap look like 4.2 sigma. But the second path, direct simulation, was catching up, and when it arrived at full strength, it did not confirm the first. It disagreed. That disagreement is the real crack in this story, and it is not the one the title first suggests. The crack may not be between the muon and the standard model at all. It may be between two ways of calculating the same corner of the standard model. To see how that came to be, we follow the first path, the one that borrows the strong force from real collisions instead of computing it. The first path is called the data-driven method, and its cleverness is worth admiring. Since the strong force contribution cannot be computed directly, the idea is to measure it instead, using a different experiment as a stand-in. The trick rests on a deep principle in physics, that the same underlying process shows up in more than one place. The very same churn of virtual quarks that dresses the muon also governs a process you can actually watch in a collider, the collision of electrons and their antimatter twins. When an electron and a positron, its antiparticle, are fired at each other and annihilate, they can turn into a burst of quarks that immediately bind into ordinary particles, mostly pairs of particles called pions. Physicists have measured the rate of this process, electron meeting positron and turning into hadrons, across a wide range of energies in laboratories around the world for decades. That measured rate is directly tied, by solid theory, to the hadronic vacuum polarization that dresses the muon. Measure the one and you can compute the other. So the data-driven method is a kind of accounting. You gather every good measurement of electrons and positrons turning into hadrons at every energy from many experiments, and you stitch them together into a single curve. From that curve you calculate the strong force contribution to the muon's anomaly. You never compute the strong force from scratch. You let nature compute it in the collider and you read off the answer. it is an elegant way around a broken calculation. This was the method behind the prediction published in the year 2020 by the Muon G2 Theory Initiative, a large international group formed to produce one agreed best value for the standard model prediction. They pooled the world's collision data, combined it with the sharp electromagnetic and weak pieces, and arrived at a single number for the Muon's anomaly. It was this number that the Fermilab measurements sat above by 4.2 sigma. For a moment, the data-driven prediction was the accepted truth, and the gap looked like a real crack. But the method has a soft spot, and it is the data itself. The final prediction is only as good as the collision measurements feeding it, and those measurements come from different experiments, at different labs, using different techniques, and they do not all agree perfectly with one another. The most important region, the low-energy collisions that produce pairs of pions, contributes the largest share of the hadronic slice, so any disagreement there matters enormously. Experiments named KLOE and Baybar, for instance, gave results that did not sit comfortably together in exactly this crucial region. For years, these tensions in the data were folded into the uncertainty and lived with. The Theory Initiative did careful, honest work combining everything, and their 2020 value was the best the data-driven method could offer. It was good enough to make the Muon's gap look like strong evidence for something new. Had the story stayed here, the headlines of the year 2021 might have held. The story did not stay here, because the second path finally arrived. A completely different way of computing the hadronic slice, one that does not use collision data at all, had been maturing for years on the world's largest supercomputers. When it produced a precise enough answer, that answer did not match the data-driven value. It sat higher, closer to the Muon measurement, and it threatened to erase the very gap that had caused all the excitement. The second path is called lattice quantum chromodynamics, and it takes the boldest possible approach. Instead of dodging the strong force, it confronts it directly by brute computational force. Quantum chromodynamics is the full theory of the strong force, the rulebook for quarks and gluons, and while its equations cannot be solved by the neat series that failed us, they can be solved another way, by approximation on a computer, if you have enough computing power. That is what the lattice method does. The idea is to chop space and time into a fine grid, a lattice of points, like the intersections on a vast piece of graph paper extended into 4 dimensions. On this grid, the strong force can be simulated numerically. The quarks live on the points, the gluons on the links between them, and a supercomputer works out how the fields behave across the whole grid, averaging over enormous numbers of possible configurations. The finer the grid and the larger the volume, the closer the simulation comes to reality and the more computing it devours. This is not a small undertaking. A serious lattice calculation of the Muon's hadronic contribution consumes months of time on some of the most powerful supercomputers on the planet, running trillions of operations to tame the roaring rapid of the strong force one grid point at a time. For years the method existed, but could not reach the precision the Muon comparison demanded. It could get the strong force slice roughly, but not sharply enough to rival the data-driven value. So it sat on the sidelines while the data-driven number ruled. Then, in the year 2020 and into 2021, a group known by the initials of their cities, the Budapest-Marseille-Wuppertal collaboration, published a lattice result of unprecedented precision. For the first time, a direct simulation of the strong force reached a sharpness that could stand beside the data-driven number, and when their value was compared, it did not agree with the collision data value. It came out higher. That single word, higher, changed everything. A higher hadronic contribution means a higher total prediction for the Muon's anomaly, and a higher prediction means a smaller gap between theory and the Muon measurement, because the measurement sits high already. The lattice result pushed the predicted number up toward the measured one, shrinking the very discrepancy that had looked like 4.2 sigma. If the lattice value was right, there might be no crack between the Muon and the standard model at all. The Muon might be behaving exactly as the theory demands, once the theory is computed correctly. So physics found itself in a genuinely awkward place. Two respected methods, aimed at the same slice of the same number, disagreed with each other by more than their stated uncertainties allowed. The data-driven method, built from decades of collision measurements, gave a lower value and a real gap. The lattice method, built from direct simulation, gave a higher value and little or no gap. They could not both be right, and the difference between them was exactly the size of the effect everyone was arguing about. This is the honest and surprising heart of the matter. The famous Muon crack, the possible sign of new physics, was suddenly entangled with a second question that had nothing to do with new particles at all. Which way of calculating the ordinary strong force is correct? The excitement about physics beyond the standard model now had to wait on a quieter, harder puzzle about the standard model itself. The crack might be in nature, or it might be in the calculation, and telling the two apart became the whole game. When two careful methods disagree, physicists do not simply pick the answer they like. They treat the disagreement itself as a clue, because both methods are supposed to be computing the same real number, and the fact that they differ means at least one of them is missing something. So the tension between the data-driven value and the lattice value became, for several years, one of the most closely watched problems in the field, more urgent in a way than the Muon gap itself. Consider what each outcome would mean. Suppose the data-driven method is right, the lower hadronic value, the real 4.2 sigma gap. Then the muon is more magnetic than the standard model allows, and the excess is the fingerprint of new physics, some heavy particle flickering in the muon's haze. That would be a historic discovery, the first solid crack in the standard model, exactly where the sensitive muon was meant to reveal it, the dream outcome. Now suppose the lattice method is right, the higher hadronic value. Then the predicted anomaly rises to meet the measurement, the gap shrinks toward nothing, and the muon is behaving precisely as the standard model requires. There is no new particle in the muon's haze. The apparent crack was never a crack in nature at all. It was an error in one way of computing the ordinary strong force, and the standard model stands once again unbroken and triumphant. Both outcomes are important, which is easy to forget in the hunt for something new. Even if the muon reveals no new physics, settling how to compute the strong force contribution to this precision is a real advance, because that same contribution matters for many other measurements. And even the disappointment carries a lesson, that our theory is even more robust than the excitement suggested. A crack that closes is still knowledge. The wonder here is honest either way. For a while the situation was genuinely unresolved, and good physicists disagreed in good faith. The data-driven method had decades of experimental grounding, but known internal tensions between data sets. The lattice method had the appeal of computing the strong force directly, but was newer, and its extraordinary precision needed to be checked by other lattice groups working independently. Neither side could simply dismiss the other. The number sat contested, and the meaning of the muon gap hung on which value would win. What was needed was a tiebreaker, a way to tell whether the collision data or the simulation was closer to the truth, and a tiebreaker existed, hiding in plain sight. The data-driven method depends on those measurements of electrons and positrons turning into pairs of pions at low energy, the crucial region where the different experiments already disagreed a little. If the collision data in that region was somehow biased low, the data-driven value would come out too low, the gap would be an illusion, and the lattice value would be vindicated. So the spotlight swung onto the collision experiments themselves, the ones measuring electrons and positrons becoming pions. Everything now turned on whether those decades-old measurements were right, especially in the region that mattered most. And just as the field was leaning on those measurements harder than ever, a new experiment weighed in with a result that made the puzzle deeper rather than clearer. The new experiment was called CMD3, and it runs at a laboratory in Novosibirsk in Russia, on a collider that smashes electrons and positrons together at low energies, exactly the energies that matter most for the muon's hadronic slice. In the year 2023, the CMD3 collaboration published a fresh, careful measurement of the crucial process, electrons and positrons turning into pairs of pions in the very region where everything hinged. The field waited to see which way it would fall. It fell in an unexpected direction. The CMD3 measurement came out higher than the earlier experiments, higher than KLOE, higher than Babar, higher than the values that had gone into the data-driven prediction. A higher rate for this process means a higher hadronic contribution, which means a higher predicted anomaly for the muon, which means a smaller gap. In other words, the new collision data pushed the data-driven method in the same direction the lattice simulations had gone, up toward the measurement, closing the crack. At first glance, this looks like resolution. If the newest and most careful collision measurement agrees with the lattice value, then perhaps the older collision data were simply a little too low, the data-driven prediction was slightly off, and the muon gap was an artifact all along. The standard model would be vindicated, the crack would close, and the strong force puzzle would be on its way to being solved. That is one honest reading. But it is not so simple, and here the story earns its complexity. The CMD3 result does not merely correct the old data, it disagrees with the old data sharply, by more than the experiment's stated uncertainties comfortably allow. KLOE and Babar and the others cannot all be right if CMD3 is right, and no one yet knows which measurement to trust. So the new result did not so much resolve the tension as relocate it. The disagreement moved from lattice versus data into the collision data itself, experiment against experiment. This is an uncomfortable place to be, because these are all careful groups using well-understood machines to measure a process that ought to be settled. When they disagree by more than they should, it means someone is underestimating a source of error somewhere, and finding it is painstaking work. The pion measurements are being scrutinized, repeated, and cross-checked with new urgency, because the meaning of the muon result rides on getting them right. Until they agree, the data-driven prediction cannot be pinned down. Notice what has happened to the shape of the whole story. It began as a clean contest, the muon measurement against the standard model prediction, with a tempting gap between them. It has become a tangle of quieter contests underneath, lattice against data-driven, and now collision experiment against collision experiment. The grand question of new physics has been wrapped inside a thicket of technical disagreements about how to compute one small, stubborn slice of an ordinary force. This is what real physics at the frontier often looks like, not a clean reveal, but a careful untangling. And yet the tangle is progress. Each new measurement, each independent lattice calculation, each re-examination of old data narrows the possibilities. The field is converging slowly on a trustworthy value for the hadronic slice, and with it a trustworthy prediction for the muon. But before we see where that convergence has led, we should ask the question that started the whole search. If the gap were real, if some new particle truly were flickering in the muon's haze, what could it actually be? Suppose for a moment that the gap survives, that when all the dust settles, the muon really is more magnetic than the standard model can account for. What could be causing it? What kind of new thing, flickering in the vacuum around the muon, would add just that sliver of extra magnetism? Physicists have spent years drawing up candidates, and the muon's anomaly, if real, would be a powerful filter on which of them could be true. The most celebrated candidate is supersymmetry, an idea that predicts a heavy partner for every known particle, a hidden mirror family. For every quark a squark, for every force carrier a partner of its own, a whole second cast of particles too heavy to have been made yet. If supersymmetric partners exist, they would flicker in the muon's haze and could nudge its magnetism upward by roughly the right amount. For decades, supersymmetry was the leading hope, elegant and motivated by other puzzles, and the muon anomaly was one of its best pieces of possible support. There are humbler candidates too. One is a new force carrier, a particle sometimes called a Z-prime or a dark photon, a cousin of the ordinary photon that couples very weakly to matter and could belong to a hidden sector of the universe, perhaps even tied to dark matter. Such a particle, flickering near the muon, would leave its own faint imprint on G-2. Another candidate is a leptoquark, an exotic particle that would let quarks and leptons transform into one another, tying together families the Standard Model keeps apart. Each candidate leaves a slightly different fingerprint, and the muon's anomaly, combined with other measurements, helps decide between them. This is the quiet power of a single precise number. It does not merely say new physics or no new physics. Its exact size constrains what the new physics could be, ruling out some candidates as too weak to explain it, and others as so strong they would have shown up elsewhere already. The anomaly is both a discovery tool and a filter. There is a sobering constraint on all of this, and it comes from the electron. Remember that the electron's magnetism agrees with theory to 12 digits, with no room for anything unknown. Whatever new particle might tug on the muon must tug on the electron far more gently enough to stay hidden in those 12 digits. This is naturally satisfied if the new physics prefers heavier particles, since the muon is so much heavier than the electron. But it means any explanation of the muon gap must also explain why the electron stays silent, and that is a real test. The great direct search for these candidates happens at the Large Hadron Collider at CERN, which slams protons together at the highest human-made energies to try to make new particles outright. So far, it has not found supersymmetric partners, or leptoquarks, or new force carriers, at least not in the ranges it has searched. That absence matters. It pushes any new particle to be either heavier than expected, or more weakly coupled than hoped, and it has taken some of the shine off the simplest versions of supersymmetry. So the candidates remain candidates. If the muon gap is real, one of these ideas, or something no one has thought of, is quietly at work in the vacuum. If the gap closes, these ideas lose one of their footholds and must look elsewhere for support. Either way, the muon has been doing exactly what a good probe should, narrowing the space of what the universe can contain. And it turns out the muon is not the only place where a possible crack has appeared. There have been others, and their fates are instructive. The muon's anomaly is the most famous possible crack, but it has not been the only one. Over the past few decades, several other measurements have drifted from the Standard Model's predictions, each raising the same hope that here, at last, was the first sign of something new. Their stories are worth knowing, because they show how often a promising crack appears, and how the field learns to tell a real one from a mirage. Consider the mass of the W boson, one of the heavy carriers of the weak force. The Standard Model predicts its mass with great precision, tied to the masses of other particles. In the year 2022, a collaboration at Fermilab called CDF announced a new measurement of the W mass, the most precise ever made, and it came out heavier than the theory predicted by a startling margin, around 7 sigma on its own. For a moment it looked like an even sharper crack than the muon, a dramatic break with the Standard Model. But the W mass story took a different turn than the muon's. The CDF result did not agree well with other measurements of the same mass made at CERN by the experiments called ATLAS and LHCb, which sat much closer to the Standard Model value. When one experiment disagrees not only with theory, but with every other experiment measuring the same thing, suspicion falls on the lone result. As of now, the CDFW mass anomaly is widely regarded as most likely an underestimated uncertainty somewhere in that one difficult measurement, rather than a true break in the theory, though the matter is not fully closed. Then there were the beauty quark anomalies, a cluster of hints from the LHCb experiment at CERN. LHCb studies the decays of particles containing the bottom quark, sometimes called beauty, and for several years its measurements suggested that these particles were decaying into muons and electrons at slightly different rates than the Standard Model demands. The theory insists the two should be treated almost identically, a principle called lepton universality. So any difference would be a real crack, and it pointed intriguingly toward the muon again. The beauty quark hints climbed as high as 3 sigma and generated tremendous excitement, with many theorists proposing new particles, leptoquarks among them, to explain them. Then, In late 2022, LHCb released a more careful analysis with more data and a better understanding of its own detector. The anomaly melted away. The decay rates for muons and electrons came back into line with the standard model, right where lepton universality said they should be. A 3 sigma crack had closed, revealed as a subtle effect in the analysis rather than a message from nature. These stories carry a clear and useful lesson. Cracks appear more often than they hold. A measurement drifts from prediction, excitement builds, and then, more often than not, better data or a corrected calculation pulls it back into agreement. The standard model has a long record of surviving these challenges, absorbing hint after hint and emerging intact. This is not cause for cynicism, but for discipline. Each fading crack teaches the field how to weigh the next one, and it puts the muon in perspective. The muon's anomaly is unusually stubborn, backed by 2 independent experiments, and a clear theoretical reason for the muon to be sensitive to new physics. But it lives in the same landscape as the W mass and the beauty quark hints, where enthusiasm must always be tempered by the memory of cracks that closed. To judge the muon fairly, we need to be precise about what our numbers really mean, and that requires understanding the strange, essential language of sigma. We have leaned on the word sigma throughout this story, and it is time to look at it plainly, because it is the language physicists use to keep themselves honest, and it is easy to misread. Sigma is a measure of surprise. It tells you how far a result sits from what you expected, counted in units of the result's own uncertainty. A gap of 1 sigma is the size of the ordinary wobble you would see by chance. A gap of many sigma is a gap that chance struggles to explain. The reason physicists need this is that every measurement fluctuates. Even if the muon perfectly matched the standard model, you would not measure exact agreement, because random noise nudges every result a little one way or the other. So the question is never simply whether the measurement equals the prediction. It is whether the difference between them is larger than the noise would naturally produce. Sigma answers that question by putting the gap and the noise in the same units. The scale is steep, which is the part that surprises people. A 2 sigma result would happen by chance about 1 time in 20, common enough to ignore. A 3 sigma result, the old Brookhaven level, happens by chance about 1 time in 700. Interesting but not decisive. A 4 sigma result is rarer still. And 5 sigma, the traditional threshold for claiming a discovery in particle physics, corresponds to a chance fluke only about 1 time in 3.5 million. The field set that bar high on purpose, having been burned before. There is a further subtlety that keeps physicists cautious, sometimes called the look elsewhere effect. If you examine many quantities, some will drift from their predictions by chance alone, the way that among enough coin flippers, someone will flip 10 heads in a row without any trickery. A 3 sigma surprise found after searching through dozens of measurements is less impressive than a 3 sigma surprise in a single quantity you set out to test in advance. The muon anomaly is of the stronger kind, a single, specific, long-predicted number, tested head-on. That is part of why it is taken so seriously. But sigma has a limit that is crucial to the muon story, and it is this. Sigma measures how far the measurement sits from a particular prediction, but it says nothing about whether that prediction is correct. If the prediction itself is wrong, a large sigma is not a sign of new physics. It is a sign that the prediction and the measurement disagree, and the fault could lie on either side. The 4.2 sigma muon gap was always a statement about the distance to one specific predicted value, the data-driven one. This is why the whole drama shifted over the past few years, from the experiment to the theory. The measurement of the muon's anomaly is now extraordinarily solid, sharpened by Fermilab to a precision no one will beat for years. The uncertainty that decides the sigma comes overwhelmingly from the prediction, and specifically from that stubborn hadronic slice where lattice and data-driven methods have wrestled. Sigma, in the muon's case, is really a measure of how well we can compute the strong force, dressed up as a measure of new physics. So when you hear that the muon gap is some number of sigma, hold it carefully. It is a real and useful number, but it is a comparison to a prediction that has been moving. As the prediction firmed up and shifted, the sigma changed with it, not because the muon changed, but because our best calculation of what the muon should be changed. Which brings us at last to where the whole question stands today, after the final measurement and the newest prediction have both arrived. Bring the two sides together as they stand now, in the middle of this decade, and the picture is clearer than it was, though not in the way the early excitement predicted. On the measurement side, the Fermilab experiment delivered its final result in the year 2025, using its full 6 years of data. The Muon's anomaly is now measured to a precision of about 127 parts per billion, a more than 4-fold improvement over the first result, and better than the experiment's original goal. It is the most precise measurement of the Muon's magnetism ever made, and it will stand for many years. That final number agrees beautifully with all the earlier results, from Brookhaven and from Fermilab's own first runs. The experiment has done everything asked of it. The measured value of the Muon's anomaly is now pinned down with confidence, its uncertainty small and well understood. On the measurement side, there is no more argument. The Muon has spoken as clearly as our instruments allow. The movement, in the end, came from the theory side, exactly where the trouble had always lived. In the year 2025, the Muon G2 Theory Initiative published a new prediction, and it was markedly different from their earlier one. Where their 2020 value had been built almost entirely from the collision data, the new value took full account of the mature lattice calculations, which had by then been confirmed by several independent groups, and of the puzzle stirred up by the CMD3 collision measurement. The new prediction came out higher, pushed up toward the measurement, and with a larger, more honest uncertainty reflecting the unresolved tensions. The effect on the famous gap was dramatic. The new, higher prediction sits far closer to the measured value than the old one did. The 4.2 sigma crack has largely closed. By the most recent reckoning, the difference between the measured muon anomaly and the best standard model prediction has shrunk to something like half a sigma, well within the range of ordinary agreement. Measured against today's best theory, the muon is behaving very nearly as the standard model says it should. So the honest headline right now is not that the standard model has been broken. It is that the apparent crack has narrowed toward nothing, and that the story turned out to be less about a new particle and more about the long, hard task of computing the strong force correctly. The excitement of the year 2021 has matured into a quieter and in some ways deeper result, a lesson in just how difficult and how important the ordinary parts of the theory can be. The wonder here is real, but it is the wonder of a theory proving tougher than expected. Yet nothing is fully settled, and it is important to say so plainly. The tension inside the collision data has not been resolved. The newest measurement of electrons and positrons becoming pions disagrees with the older ones, and until that is sorted out, the prediction cannot be considered final. The lattice calculations, though increasingly consistent, are still being refined and cross-checked. The gap is small today, but the ingredients that set its size are still in motion. It remains possible, if less likely than it once seemed, that a real, smaller discrepancy will survive. This is where the muon leaves us for now. Not with a shattered standard model, and not with a closed case, but with a theory that has bent under the most precise test yet devised, and so far held. The crack the title promised turned out to be, most likely, a crack in our ability to calculate rather than a crack in nature. And that raises a fair and quiet question. If the gap has narrowed to almost nothing, why did any of this effort matter, and why should anyone keep measuring at all? It is a fair question, and it deserves an honest answer, because at first glance the story can look like a letdown. 2 great experiments, a ring hauled across a continent, decades of calculation, a wave of excitement, and in the end the crack narrows toward nothing, and the standard model stands. If the point was only to find new physics, and no new physics was found, was the whole enterprise a disappointment? It was not, and understanding why goes to the heart of how science actually works. Start with what was gained, even in apparent failure. To chase the Muon's anomaly, physicists were forced to compute the strong force contribution to a precision never approached before, and to do it by two independent methods, lattice and data-driven, that could check each other. That effort has sharpened our command of the strong force itself, the least tractable of the forces, in ways that ripple out to many other measurements. The Muon pushed the whole field to compute better. That knowledge does not evaporate because the gap closed. Consider too what a closing crack actually tells us. Every time the standard model survives a precise test, we learn that it holds to a new depth, and that whatever lies beyond it must be subtler or heavier or more weakly coupled than we hoped. That is real information about the universe. It rules out whole families of possible new particles, or pushes them into narrower corners. A theory that passes its hardest test is not a boring result. It is a boundary drawn more sharply around the unknown, telling future searchers where not to look. There is also the simple fact that the question is not truly closed. The tension in the collision data remains unresolved. The lattice calculations are still being refined. The measurement is final, but the prediction it is compared against is still settling, and it is not impossible that a small real discrepancy will emerge from the dust. Precision physics does not end with one result. It is a long conversation, and the Muon's part in it is still being spoken. Beyond the Muon specifically, there is the deeper reason the whole approach matters. The great open questions remain exactly as open as before. We still do not know what dark matter is, or how gravity fits with the quantum world, or why matter survived over antimatter. The standard model still cannot answer these, so something beyond it must exist, waiting to be found. Precision measurements like the muons are one of the few tools sharp enough to feel that something before any machine can make it directly. The method is sound even when a particular search comes up quiet. This is the patient temperament that precision physics demands. You measure a number to the 9th digit, knowing the answer may simply confirm what you already believed. You build a ring, move it across a country, run it for 6 years, and the reward may be a crack that closes. And you do it anyway, because the only way to find the edge of a theory is to test it exactly where it might break, over and over, until either it fails or your confidence in it deepens. Both outcomes are worth the effort. Both are how we learn. So the Muon's magnetism was never a gamble that paid off only if new physics appeared. It was a measurement worth making for its own sake, a way of asking the universe a very precise question and listening carefully to the answer, whatever it turned out to be. And the answer it gave, though quieter than the dream, still teaches us something about our place in the cosmos and about the strange, restless nothingness that fills all of space. We began with a compass needle settling toward north, pulled by a field no one can see, and with the claim that one of the smallest things in the universe behaves the same way. Let us return to it now and answer the title's question in the plainest words. The tiny crack was the small gap between how magnetic the muon is measured to be and how magnetic our best theory says it should be. And that crack, tested to the 9th digit and pushed as hard as human effort allows, has so far narrowed toward nothing rather than bringing the standard model down. But look at what we passed through to reach that plain answer. We found that a particle can be a magnet without spinning, that its magnetism follows from Dirac's marriage of quantum mechanics and relativity, and that the clean hole number 2 hides a faint tail. We found that the tail is the fingerprint of empty space, which is not empty at all, but a restless froth of particles flickering in and out, pressing on plates, shifting atoms, dressing every charge in a haze of activity. The muon's magnetism is a way of measuring that froth. We found that the muon, the electron's heavy cousin, is tens of thousands of times more sensitive than the electron to whatever heavy, hidden things might lurk in that froth, which makes it our finest listener for physics beyond the known. And we watched the search unfold honestly, from a whisper at Brookhaven to a near shout at Fermilab, and then the surprising turn as the drama moved from the Muon itself to the stubborn task of computing the strong force, where the crack quietly narrowed. Here is the piece worth carrying with you. When you measure the magnetism of a single muon, you are, in effect, taking a census of everything that exists. Every particle in the universe, known or unknown, light or crushingly heavy, contributes a little to the froth around that muon, and so leaves its faint mark on this one number. To measure G-2 to the 9th digit is to ask the vacuum to tell you, in a single figure, what it is made of. That the answer so far matches our list is not a small thing. It means our list, for all its gaps, is remarkably complete, and yet the gaps are real, and they are enormous. We still do not know what most of the universe is made of. Dark matter holds the galaxies together with a gravity we cannot source. Dark energy pushes the cosmos apart for reasons we cannot name. Gravity itself has never been fit into the quantum picture, and the very fact that matter exists, that the early universe did not simply annihilate into light, has no explanation in our theory. Something is out there, beyond the standard model, and the muon's magnetism is one of the doorways through which we keep hoping to glimpse it. That is why the muon matters, even now, even with the crack narrowed. It is a small, spinning probe that samples the whole vacuum and reports back, and we have learned to read its report to 9 digits. The next digit is already being pursued, in new experiments and sharper calculations, and somewhere in those digits the real crack may still be waiting, or may never come. Either way, we will have asked the universe an honest question and listened to the whole answer, so the next time you watch a compass needle swing north, pulled by a field you cannot see, remember that the same quiet physics runs all the way down into a particle 200 times lighter than a proton spinning in a ring, its faint magnetism carrying news of everything that is. The invisible is not empty, it is full, and it is speaking, and we are slowly, patiently, learning how to hear it.